Okay, so we continue with Yann Guggisberg, who will tell us about instantaneous Hamiltonian displaceability and arbitrarily symplectic squeezability for critically negligible sets.
Yes, so thanks a lot for the invitation. I'm very happy to talk today. It's actually my birthday, so it's a nice way to do something special today. So yeah, I'm gonna talk about Hamiltonian displaceability and squeezability. So the plan is, I'm gonna try to ask a vague question that's gonna motivate what I'm gonna talk about. Then define a bit the things that I'm using, so the Hausdorff dimension, displacement energy, then talk about squeezability and a potential nice applications to barriers and non-barriers in symplectic manifolds. So this is all based on a joint work with my supervisor, Fabian Ziltener. And the vague question that motivated it is the following. So what is the smallest size of a subset of a symplectic manifold that carries some symplectic geometry? So there's a bit this philosophy that the interesting symplectic geometry starts happening at half the dimension because it's the dimension of Lagrangians. And as you know, in Lagrangians capture symplectic geometry in many, many interesting ways. So for me, in this talk, size will be interpreted as the Hausdorff dimension, which I'll remind what it is in a few moments. And carries symplectic geometry will be two different things. First, it will be has positive displacement energy, so it's not that easy to displace the subset from itself in some sense. And the other will be it's not easily squeezable into small subsets. So this is the plan, and here's now the first precise version of that vague motivation question, which is what is the smallest Hausdorff dimension of a subset that has positive displacement energy? So let me first say, remind you what I mean by Hausdorff dimension. If I have a metric space and a non-negative number, I can call this metric space S Hausdorff negligible. If for every positive epsilon, I can find a countable collection of sets that covers my set X, and such that this sum of the diameters of the sets to the power S is smaller than epsilon. So basically as small as I want. So another equivalent way of saying this is that the Hausdorff outer measure, the S Hausdorff measure is 0. And then the Hausdorff dimension will be the smallest such number. So the smallest S, the infimum over all S, such that X is S negligible. And so let me give you a few examples to say what this means. So obviously for some manifolds, it's just going to be the usual dimension that we have. So it's an extension of the notion of dimension to other sets. It's often used for fractals. So the excluded third Cantor set has Hausdorff dimension log 2 over log 3. I think the Sierpinski triangle is the reciprocal, so log 3 over log 2. If you have a space filling curve, this is going to be the dimension of the curve will be the Hausdorff dimension of the space. There are all sorts of things. People, I think, try to compute the Hausdorff dimension of coastlines of different countries. So you can do this for very general sets, is maybe my point. So this is the first part. And now I'm going to talk about displacement energy. So when I have a time-dependent Hamiltonian function, I denote by phi the corresponding flow. And I look at the well-behaved Hamiltonian function, which means the ones for which the flow is defined at least up to time 1. And then on this set, I can define the following energy for the Hamiltonian, which is this integral of a supremum minus the infimum. It's also often done for a compactly supported Hamiltonian, but it's also possible to do it this way. I guess it depends on what you want to do precisely, but this won't matter too much in the rest of the talk. And then the displacement energy of a subset of a symplectic manifold is just the smallest energy of a Hamiltonian with which I can displace the subset from itself via a Hamiltonian diffeomorphism, which means a time one flow map of H. And so if I come back now to my question, I want to look at subsets that have small Hausdorff dimension and still positive displacement energy. And there is this result by Chekhanov in 98. It says, if M is a symplectic manifold that is geometrically bounded, then every closed Lagrangian has positive displacement energy. So as long as the manifold is, let's say, reasonable at infinity, you have that Lagrangians are not easy to displace from each other. So this is some rigidity. This gives an upper bound for the question when you have this assumption of geometrically bounded. And what we looked at is basically the other side, the flexible side. So we try to look at the lower bound, which means asking the question, when are sets easily displaceable from each other? So we define the following thing. So two sets are called instantaneously C-infinity displaceable if every weak C-infinity neighborhood of the identity has a Hamiltonian diffeomorphism that displaces A from B. So in particular, if I take A equals B, this will mean that A has displacement energy 0. And to be able to do this, we needed one more assumption to make our subsets not too wild, and this is the following thing. So I call a metric space countably n-rectifiable if there exists a map that is from a subset of Rm to X that is surjective and locally Lipschitz. So since my set is going to be the image of something locally Lipschitz, it's reasonable in that sense. Maybe a small remark about this term of countably n-rectifiable. This is what it's called in Federer's geometric measure theory book, but in other books, it's the same definition up to a 0 Hausdorff measure set, but our results doesn't work with that additional up to a 0 measure set. So I guess I'm really talking about strictly countably n-rectifiable in that sense. And then here is the result. So if you have a subset of R2n that is countably m-rectifiable for some m between 0 and 2n, and B is 2n minus m negligible in the Hausdorff sense that we saw before. So the complementary negligibility somehow. Then you can find a linear function that is actually time independent, such that for almost every t, the time t flow displaces A from B. So in particular, you can take t as small as you'd like. And so this has the following corollary, that if A is both countably n-rectifiable and n-negligible, then it has 0 displacement energy. And now this gives a lower bound of n as well when you add these assumptions of countable n-rectifiability.
So you say H is linear, so the flow is just translation, or
Exactly, yes.
but I mean then H is not bounded, right? So
No.
So the spoon will be infinity. So how do you define the energy in this case?
So the integral, where is it now? Here, this integral is actually measurable even for non-compactly supported Hamiltonian. So it could be infinity, but you can actually do it. still in this way and then talk about the displacement energy.
But the displacement energy would be infinite in this case.
I mean,
Okay, maybe.
I guess another way of saying this, if you would want to take compactly supported things, if you assume that my two sets are compact, then you can cut things off at infinity, before infinity, let's say, yeah. Did it make sense, or did I miss your question?
Okay, yeah, thank you. I think it makes.
So yeah, one word about the proof, because it's actually not too hard. If you look at the function from R to N to R to N, R to N times R to N to R to N, that just takes the difference of two vectors. Then with our assumptions on A and B, the image under that map of the set A times B is gonna have 0 Lebesgue measure, which means that translating A by almost every vector will be disjoint from B. And then that's how you can find your vector V such that the translation always displaces A from B.
So, excuse me, so is this symplectic result? So does symplectic structure in any way enter this result?
Can you
Because, I mean,
repeat?
just linear translations, right?
Yeah, it's just a linear translation, yeah.
So there is no, it's not a statement in symplectic geometry, right?
No, it's actually measure theoretic in nature
I see.
somehow.
Okay, thank you.
And yeah, now let me talk about squeezability. So if I have two symplectic manifolds M and M prime of the same dimension to N and a compact subset of M, I say that S symplectically embeds into M prime if I can find a neighborhood of S such that an open neighborhood such that this symplectically embeds in the usual sense. And then I say that S is arbitrarily symplectically squeezable if it symplectically embeds into every open neighborhood of the origin in R to N. So by Darboux, it embeds into anything, basically, hence the name squeezability. Another question too is, which is another version of that vague question I had at the start, and it is, what is the smallest Hausdorff dimension of a not arbitrarily squeezable subset of R to N? And known results in that direction. So for isotropic submanifolds, let's say closed submanifolds, it's not too hard to show that you can squeeze them. And with Gromov's isosymplectic embedding theorem, you can also do this for symplectic, closed symplectic submanifolds of codimension at least 2. There's also that nice result of the symplectic hedgehog theorem by Hermann, that if you're in dimension at least 4, and you look at the torus times the interval 0, 1, so kind of the star-shaped set around the origin that contains the Lagrangian torus, then this does not symplectically embed into the standard symplectic cylinder. And this has Hausdorff dimension n+1. So n+1 is a upper bound, but you can do better. You can find an n-dimensional subset for which this doesn't work. This is what Fabian did with Jan Swoboda a bit more than 10 years ago. Also in dimension at least 4, you have a compact closed subset of the ball of radius square root of 2 that does not symplectically embed into the cylinder. And this set is a closed Lagrangian union with the image of a two-sphere. And once again, in this project, we looked at the flexible side. So when are things easily squeezable? And this is the results, that every compact, countably n-rectifiable and n-negligible subset is arbitrarily squeezable. And the proof actually uses the displacement result from before. Let me try to give you a flavor of it with some pictures. So I look, let's say, at the first planar factor of R2n, so the first two coordinates. And since my set is compact, I can make it fit in a box. And then I can, in dimension 2, symplectic is the same as volume preserving, so I can move my set around so that I have this slit in the middle. And now that my set, I mean, the projection of my set to the first two coordinates fits in this box, I can look at a shear, a nonlinear shear of the plane. And what I'm going to do is apply it to the top part. So I basically do nothing on the left, but on the right, I push everything down by half the size. At this point, the set might intersect itself, but that's where the displacement result comes in, that if I consider the lower part and the top part as two different sets, then one of them is n-negligible, the other is countably n-rectifiable. So with a very small Hamiltonian diffeomorphism, I can basically remove the self-intersection. And what I've gained now is the area in the top right corner. And I can repeat this a finite number of times, but as many times as I want for every planar vector until my set fits into the box that I want. That's basically the idea of the proof. And a potential nice application of this is to barriers. So Lagrangian barriers are Lagrangian manifolds that always intersect with symplectically embedded balls of a given radius. This idea was introduced by Balbiran. He showed that some CW complex, Lagrangian complex, was a barrier. And this means that if you remove the Lagrangian from the symplectic manifold, then the Gromov width goes down. So the Gromov width is the size of the biggest ball that you can embed symplectically. And since those balls have to intersect, then you make the Gromov width go down. And yeah, this notion is quite an exciting one. There is a lot of recent papers. Here are a few. So there's one by Sakel, Song, Vaul Gunnesen Zhu, one by Brendel Schlenk, and by Obstein Schlenk, all from this year. And the same thing has also been done for symplectic manifolds. So Chaim Kislev, Hind, and Ostrover looked at union of symplectic planes of codimension 2, and it's the same idea that balls have to intersect those symplectic manifolds. And once again, here we are on the flexible side, so using the same technique of crumbling my set to a very small box, we could have something like this, that if a closed subset of, let's say, the unit ball has the correct rectifiability and negligibility properties, then it should be possible to make it fit into something very small, push that very small thing to close to the boundary with the Hamiltonian diffeomorphism, and then you would have that the Gromov width of the ball is the same as the Gromov width of the ball without that set. So in that sense, it would be a non-barrier. And I think that's it. Thank you.
Thank you. Any questions?
So in the application to the barriers, the Hamiltonian needs to be completely supported, I assume.
Yes, yeah. You have to cut it off before the boundary of the ball. Yeah, yeah.
So, and is it obvious how to make your construction, how to, is it just the usual cutoff near the boundary, or does it create problems?
I think there are a few details that you need to look at to make sure that everything works out. Maybe you have to even ask that the set is n-1 rectifiable, for example, and then use, instead of just a shear, maybe you need to use a Hamiltonian isotopy and remove the self-intersection from the image of the whole isotopy. So 0, 1 times the set. I think there are a few subtleties. It shouldn't cause any major problems, but I think to write things down carefully, you do need to think a bit, yeah.
Thank you.
Yes, thanks for the talk. Could you go back to your result where you have a Lagrangian and the sphere glued to the Lagrangian, two sphere glued to the Lagrangian?
Yes.
I somehow
This one.
I somehow missed that. But so why does this not work just with the Lagrangian? Why do you have to glue?
Oh, that's a good question. I have to say I read the paper a long time ago and I'm not sure I remember.
Because it's easy. I mean, Lagrangian have positive capacity, so you cannot embed them in something too small anyway. I mean, and I don't see what two sphere adds in the.
So
Yeah,
Clifford torus with area 1, so of radius 1 kind of, yeah. So it sits exactly in the ball of radius square root of 2, right? Because
Yeah,
1 plus 1 is 2. No? So then what Claude says, yeah, it's theorem of Sikorov probably, yeah. So that you cannot squeeze Lagrangian submanifold into a cylinder.
Yes.
Yes, so
yeah.
that's.
And I don't see what a two sphere could add, because the two sphere, at least in large dimension, is completely invisible, as you explained, actually, from the symplectic point of view. So maybe the result is slightly, well, okay. The result maybe is.
Yeah, sorry, I'm not sure. But that's a good point, yeah.
Okay, thanks.
Okay, so thank you, and thank you for all the speakers today.